Welcome students, this is lecture 8 in the topic of indefinite integration. Now we will be looking into techniques involving reduction formula. Now if we were to be given a question of this fashion to integrate, integral sine raised to the power of mx times cos raised to the power of nx times dx. Now if n is odd, then we make the substitution for sin x. If m is odd, we make the substitution for cos x. So this is an important point that you will have to know. So what we will do in this particular phase is that we will be using the concept of this, which I have just mentioned to you, in solving questions. So let me just start off with this illustration example. We are expected to integrate sine raised to the power of 5x times cos raised to the power of 4x times dx. Now in this case clearly m is odd, so we would take cos x is equal to t. So this would mean differentiating, I would have now negative sin x times dx is equal to dt. So which in turn would mean sin x dx is equal to negative dt. Now what I wish to do is I would rewrite sine raised to the power of 5x as sine raised to the power of 4x times cos raised to the power of 4x times sin x dx. So this is equal to, what we can do is we can now rewrite sine raised to the power of 4x as sine squared x times sine squared x followed by cos raised to the power of 4x times sin x dx. This is equal to, I'm going to rewrite sine squared x as 1 negative cos squared x times 1 negative cos squared x times cos raised to the power of 4x times sin x dx. Now what we can do is we can now make the substitution. So in place of cos x it is t, so it's going to be 1 negative t squared times 1 negative t squared times, this is cos raised to the power of 4, so it's going to be t power 4 times sin x dx is negative dt. So I place a negative sign and I have a dt here. So we will have to make the simplification. Now this is nothing but integral. Now I can rewrite this as 1 negative t squared raised to the power of 2 times t power 4 times dt, which is nothing but, if I were to expand this, I would get 1 negative 2 times t squared positive t raised to the power of 4 times t raised to the power of 4 times dt, right? So this is going to be, I'm going to distribute t to the power of 4, and that would give me t raised to the power of 4 negative 2 times t raised to the power of 6 positive t raised to the power of 8 times dt. So this is equal to, if I were to integrate this, I would get t raised to the power of 5 divided by 5 negative t power 7 divided by 7 positive t power 9 divided by 9. But my t is cos x. If I were to take this as 2, therefore I can rewrite 2 as the following. So that is equal to negative, so let me just make the substitution, cos raised to the power of 5 x divided by 5 negative 2 over 7 times cos raised to the power of 7 x positive cos raised to the power of 9 x divided by 9, and we can add the arbitrary constant. So this is the solution. Of course, if you want, you can distribute the negative sign. If I were to do that, I will have to start with this 2 over 7, which is a positive term, cos raised to the power of 7x, and followed by everything else would be negative. So this is going to be negative raised to the power of 5x divided by 5 negative cos raised to the power of 9x divided by 9, which is equal to, of course, what I wish to do is I would like to take cos out. So if I were to take cos raised to the power of 5x out, and I can't take anything common out with regard to the quantities in the denominator, so this would give me, I would get cos squared x with a 2 there, so 2 times cos raised to the power of 2 times cos raised to the power of 2x, and this is going to be negative 1 over 5 and followed by cos raised to the power of 4x divided by 9. This is what I've got. Now of course we can render some order, and that would be if we were to start from the lowest term. So I can place cos raised to the power of 5x over here, and I can start with negative 1 over 5 followed by positive 2 times cos squared x followed by negative cos raised to the power of 4x. Of course we got the 9 as the denominator. So depending on what you want, it's up to you. So this is a good place to add the arbitrary constant c and draw the red line. So this is the solution to this question. So we will move on to the next question, students. This is question number 2. We are expected to integrate integral sine raised to the power of 2 over 3x times cos raised to the power of negative 8 over 3x dx. Now clearly we can see that the powers of sine and cos is rational in nature. Now whenever you get a rational power, you will have to make the substitution for tan x. In other words, you should try to convert the integrand to have tan. So that is our objective. So having that as my objective, what I wish to do is I would like to divide the quantity by cos raised to the power of 2 over 3x so that I can get a tan there. So this is going to be sine 2 over 3, in other words sine raised to the power of 2 over 3x divided by cos raised to the power of 2 over 3x times cos raised to the power of negative 8 over 3 times x. But since I got cos raised to the power of 2 over 3x, I placed it there. I got to neutralize that, so I'm going to multiply it by cos 2 over 3x times dx. So this is what I've got. Now this can be rewritten as integral tan raised to the power of 2 over 3 times x. Now these two things can be coupled together, right? You got negative 8 over 3 added with 2 over 3, which is going to be negative 6 over 3, which is nothing but negative 2. So this is going to be cos raised to the power of negative 2x dx. But what is this? I can rewrite this as 1 over cos squared x times dx, right? But what is 1 over cos x? That's nothing but, this is going to give me tan 2 over 3x times 1 over cos squared x is going to be secant squared x dx. Now what I wish to do is, let me rewrite this in this fashion: tan x raised to the power of 2 over 3 times secant squared x dx. So let me make the substitution. As I mentioned to you, make sure that you get a tan there. So if we were to get a tan, the substitution would be, let tan x be equal to t. I differentiate this, I get secant squared x dx is equal to dt. So this is equal to t raised to the power of 2 over 3 secant squared x dx, which is nothing but dt. So this is straightforward. So this is going to be t raised to the power of 2 over 3 positive 1 divided by 2 over 3 positive 1, which is nothing but t raised to the power of 5 over 3 divided by 5 over 3, which is nothing but 3 over 5 times t raised to the power of 5 over 3. But my t is tan, so this is going to be 3 over 5 times tan raised to the power of 5 over 3x positive c, and this is a good place for us to draw the red line. So this is a beautiful question, students. I hope you can practice this and achieve mastery. Let's do one more question in the same type. So we expected to integrate integral sine x raised to the power of 1 over 3 times cos x raised to the power of negative 7 over 3 times dx. Now clearly the powers are rational, so I would like to, in fact I would have to have a tan x here, because the substitution should be done in this fashion. So what I will do is I will divide by This is going to be sine raised to the power of 1 over 3x. I'm going to divide it by cos raised to the power of 1 over 3x times cos raised to the power of negative 7 over 3x times, I need to neutralize this cos, so it's going to be cos raised to the power of 1 over 3 times x times dx. Now this is going to be integral sine over cos, that's going to be tan raised to the power of 1 over 3 times x, and this is negative 7 over 3 added with 1 over 3, which will give me negative 6 over 3, which is nothing but negative 2. So this is nothing but cos raised to the power of negative 2x times dx. I can rewrite this as integral tan x raised to the power of 1 over 3 times cos raised to the power of negative 2x. That's going to be 1 over cos squared x times dx. Now this is rewritten as integral tan x raised to the power of 1 over 3 times 1 over cos squared x is nothing but secant squared x dx. Now let me make the substitution for tan. Let tan x be equal to t. I differentiate this. I get secant squared x dx is equal to dt. I substitute for tan. This is going to be t raised to the power of 1 over 3. Secant squared x dx is dt. I integrate this. I get t raised to the power of 1 over 3 positive 1 divided by 1 over 3 positive 1, which can be rewritten as t raised to the power of 4 over 3 divided by 4 over 3. I flip it. I get 3 over 4 times t raised to the power of 4 over 3, but my t is tan x, so this is going to be 3 over 4 tan raised to the power of 4 over 3x positive c, and this is a good place for us to draw the red line. So this is a beautiful question. I hope you understood this. So we'll move. Students, we are given a beautiful question. We are expected to integrate this. In this case, m is even, n is even. So we need to adopt a different approach. Now what I'll be doing is I will multiply and divide by 4. So this is going to give me 4 times sine squared x cos raised to the power of 4x dx over 4. I can take this 4 out, so it's going to be 1 over 4 times integral 4 times sine squared x times cos raised to the power of 4x. I'm going to write it as cos squared x times cos squared x dx. So let me rewrite this as 1 over 4 times integral. Now this can be rewritten as 2 times sin x cos x raised to the power of 2, right? I'm just clubbing these two together, times cos squared x times dx. Now we know that sin 2x is equal to 2 sin x cos x. We know this formula, right? So just substitute that formula there. That's going to be 1 over 4 times integral sin 2x raised to the power of 2 times cos squared x. Also, cos squared x is nothing but 1 positive cos 2x divided by 2. So I'll be substituting that. So it's going to be 1 positive cos 2x divided by 2 times dx. So this is equal to, now I can bring the square inside, so that would give me sin squared 2x times, now this 2 can be taken out. Okay, so if I were to do that, that would give me 8, and this is going to be 1 positive cos 2x times dx. Now let me show you this. Sin squared x is equal to 1 negative cos 2x over 2, and if I were to take x is equal to some 2t, let us assume that this is going to be sin squared 2t is equal to 1 negative cos of 2, in place of x is going to be 2t divided by 2, which is equal to 1 negative cos 4t divided by 2, which is nothing but sin squared 2t. Would like to distribute sin squared 2x first. So that's going to give me sin squared 2x times dx positive. This is going to be sin squared 2x times cos 2x. So you got this dx here. So if I were to split this, this is going to give me 1 over 8, and let me place it in this fashion. Integral sine squared 2x dx, positive integral sine squared 2x cos 2x dx. That's fine. Now I will replace this formula over here. So this is going to be 1 over 8 times integral 1 negative cos 4 times x divided by 2 times dx, positive integral sine squared 2x times cos 2x times dx. Now if I were to split this is going to be equal to 1 over 8 integral dx. In fact, I can bring the 2 out, and this would be dx negative 1 over 2 times integral cos 4x times dx, positive integral sine squared 2x times cos 2x times dx. Now if I were to take sine 2x is equal to t, if I were to differentiate this is going to be 2 times cos 2x dx is equal to dt. So cos 2x dx is equal to dt over 2. So I can substitute this over here. So this is going to be 1 over 8, 1 over 2 times, I integrate dx, I get x, I integrate cos 4x, I get sine 4x, coefficient of x is 4, place that. This is going to be sine 2x is t, so t squared, cos 2x dx is equal to dt over 2, so place that. So this is going to be 1 over 8 x over 2 negative sine 4x over 8 positive 1 over 2 times t raised to the power of 3 divided by 3, right? So t is sine 2x, so that's going to be 1 over 8 x over 2 negative sine 4x over 8 positive 3 times 2 is 6. This is going to be sine cubed 2x divided by 6. So now you can bring the 8 inside, so that's going to be x over 16 negative sine 4x over 64 positive sine cubed 2x over 48 positive arbitrary constancy. I can see that this is a little bit lengthier problem, but still with some practice we would be able to achieve the solution, and this is a good place for us to draw the red line. We'll move on to the next question, students. Students, we are expected to integrate this integral sine raised to the power of 4x over cos squared x dx. Now I'm going to rewrite this as integral sine squared x raised to the power of 2 divided by cos squared x times dx. Now we know that sine squared x is 1 negative cos squared x, and this has to be raised to the power of 2 divided by cos squared x times dx. Now if I were to expand this is going to be integral 1 negative 2 times cos squared x positive cos raised to the power of 4x divided by cos squared x times dx. Now I'm going to split this by algebraic property. So this is going to give me 1 over cos squared x negative 2 times cos squared x over cos squared x positive cos raised to the power of 4x divided by cos squared x times dx. So this is equal to 1 over cos squared x is secant squared x. This is going to be negative 2. This is going to give me cos squared x times dx. I can rewrite this as integral secant squared x dx negative 2 times integral dx positive integral cos squared x dx. So this is what I've got. So now what I'm going to do is I would like to use this space here. Okay. So we are expected to integrate this integral secant squared x dx negative 2 times integral dx positive integral cos squared x dx. Now integral of secant squared x is going to give me tan x. This is going to give me x. Now cos squared x, I'm going to write it as 1 positive cos 2x divided by 2 times dx. So this is equal to tan x negative 2x, positive 1 over 2 can be taken out, that's going to give me dx. 1 over 2 is already taken out, so this is going to give me cos 2x dx. So this is equal to tan x negative 2x, I integrate this, I would get x over 2, I integrate this, I would get sine 2x divided by 2. So this can be rewritten by simplification. This is negative 2x and you got x over 2. So if I were to simplify this, let me just simplify that. That's going to be negative 4x positive x divided by 2, which is going to give me negative 3x over 2. So I have a tan x negative 3x over 2, and this is going to be sine 2x divided by 4 plus arbitrary constancy. Now if you want to rewrite this, probably you can start with sine 2x divided by 4 followed by tan x and then negative 3x over 2 plus arbitrary constancy, and this is a good place for us to draw the red line. So we'll move on to the next question, students. Since we have a beautiful question to solve, the question is integral of sin x positive cos x over sin x times cos x times dx have to be evaluated. This looks simple, but if you are going to be adopting the normal way of, or the normal technique of substitution, you are not going to be solving this question at all, because this requires a special type of substitution. So that would be, we would have to take the substitution as follows. So we would take sin x negative cos x to be equal to t. So I differentiate sin x, I get cos x. I differentiate cos x, I get negative sin x, and that has to be multiplied with dx, which is equal to dt. So now rewriting, this is going to be cos x positive sin x times dx is equal to dt, which is actually sin x positive cos x times dx is equal to dt. So which is present in the numerator. Now we would have to get the denominator. So what I would like to do is, let us consider the substitution. We have taken sin x negative cos x to be equal to t. So what I'm going to do, I'm going to square both sides. This would give me sin squared x positive cos squared x negative 2 times sin x cos x is equal to t squared. If I were to add these two, this would give me 1 negative 2 times sin x cos x is equal to t squared. Let me push this one to the other side. This in turn would give me negative 2 times sin x cos x is equal to t squared negative 1. I want to get rid of this negative sign, so it's going to be 2 times sin x cos x is equal to 1 negative t squared. I want to bring this 2 down, so that's going to be sin x cos x is equal to 1 negative t squared over 2. So in place of sin x cos x, I've got 1 negative t squared divided by 2. So I would substitute that. So this is going to be, in place of sin x positive cos x times dx, I can substitute this value dt, and in place of sin x cos x, I need to substitute 1 negative t squared divided by 2. If I were to flip it, this is going to be 2 over integral dt over 1 negative t squared. Now I can actually rewrite this as 2 times integral dt over 1 squared negative t squared. Now this is similar to our integral dx over a squared negative x squared, which is nothing but 1 over 2a times ln of a positive x divided by a negative x, positive arbitrary constancy. So I would use this formula over here. So that's going to be equal to 2 times of 1 over, my a is 1, ln of 1 positive t divided by 1 negative t, right? Now I'm not placing the arbitrary constant as yet, so this is equal to 2 can be cancelled, giving me ln of 1 positive t divided by 1 negative t. Now my t is sin x negative cos x. So this is going to be ln modulus of 1 positive sin x negative cos x divided by 1 negative of sin x negative cos x. So if I were to rewrite this, this is going to be ln of 1 positive sin x negative cos x divided by negative positive. So I can rewrite this as 1 positive cos x negative sin x with the arbitrary constant c, and this is a good place for us to draw the red line. So this is a beautiful question, students. I hope you understood this. Students, we have been given a beautiful integral to evaluate. We've been given integral root of tan x positive root of cot x times dx. Now this is a nice question. It looks simple, but if we are going to be adopting the usual method of substitution, it wouldn't be easy to solve this. So what I'm going to do is I'm going to follow the technique that I've just mentioned above. So I would rewrite tan x as sin x over cos x. So it's going to be root of sin x divided by root of cos x, and I will write cot x as root of, in fact cot x is cos x over sin x. Since I have root of cot x, I'm going to write it as root of cos x over root of sin x times dx. Now this is equal to integral. Now if I were to take the LCM, this is going to be root of sin x times root of cos x. Root of cos x and root of cos x gets cancelled, giving me root of sin x. That has to be multiplied with root of sin x. Hence I would get a sin x. Similarly, root of cos x times root of cos x would give me cos x times dx. Now this can be rewritten as integral sin x positive cos x times dx. Root of sin x times root of cos x is going to be square root of sin x times cos x. Now I'm going to make the following substitution. Let sin x negative, I know there is a positive here, you get a positive here, make a substitution with a negative. So this is going to be let sin x negative cos x be equal to t. So if I were to differentiate this, I get cos x positive sin x times dx is equal to dt. Okay, I have got the numerator. In fact, let me rewrite it as sin x positive cos x times dx so that you can understand in a more clear manner. So clearly the numerator is there, so that substitution is fine, but we need to get the denominator. If I were to take this as sum 2 squaring 2, okay, we get, so what do we get when we square 2? This is going to give me sin squared x positive cos squared x negative 2 times sin x times cos x, right? And on the right side is going to be t squared. Now sin squared x positive cos squared x is 1, followed by negative 2 times sin x cos x is equal to t squared. I push the 1 to the other side. That would give me negative 2 times sin x cos x is equal to t squared negative 1. I want a positive sin x cos x, so I need to get rid of the negative sign. So that in turn would mean I now have 2 times sin x cos x is equal to 1 negative t squared. I don't want this 2 here, so I push the 2 to the right. So that would mean I get sin x cos x is equal to 1 negative t squared divided by 2. So in place of sin x cos x, I've got this term. So let me substitute that. So therefore, if I were to take this 3 can be now rewritten as integral sin x positive cos x dx is dt. Substitute that. In place of sin x cos x, I need to substitute 1 negative t squared over 2. So that's going to be 1 negative t squared over 2. So that's going to be root of 2, right? So I can push the root of 2 to the numerator. So this is going to be root of 2 times integral dt divided by root of 1 negative t squared. Now we know that integral dx over root of 1 negative x squared is equal to sine inverse of x positive c, right? We know this formula. So using this formula there, this would give me root of 2 times sine inverse of t. But my t is sin x negative cos x, right? Sin x negative cos x. So substitute that. That's going to be root of 2 times sine inverse of sin x negative cos x plus arbitrary constancy. So this is the rough side. And this is a good place for me to draw the red line. So that's the solution, students. I hope you understood this question. We will move on to the next one. Students, now we are going to see the reduction formula for sin x. So let me write that down, reduction formula for sin x. So before we could head on to observe on to understand the reduction formula for sin x, let me show you the following deduction for sin x. Now suppose you got sine squared x dx and you are expected to integrate. You can always convert this as 1 negative cos 2x over 2 times dx, right? And then you can integrate this. Now suppose if you were given integral of sine cubed x dx, then what you can do, you can use this formula. Sine 3x is equal to 3 times sine x negative 4 times sine cubed x. So from here I can write sine cubed x with a 4 there to be equal to 3 times sine x negative sine 3x. So therefore sine cubed x is 3 times sine x negative sine 3x divided by 4. And then I can substitute that over here. So this is going to be 1 over 4 times integral of 3 times sine x negative sine 3x times dx. So this is easy to integrate, as also this quantity which we see here is easy to integrate. So 1 is achievable, 2 is achievable because of the reduction. Now imagine you are asked to integrate integral of sine raised to the power of 4x dx. I can rewrite this as sine squared x raised to the power of 2 times dx. Then I can rewrite this sine squared x as 1 negative cos 2x over 2 raised to the power of 2 times dx. Then I can expand this as 1 negative, this is going to be raised to the power of 2, right? So it's going to be 1 negative 2 times cos 2x positive cos squared 2x times dx. So this again is easy to integrate, right? Because I know how to rewrite cos squared x as 1 positive cos 2x, and it is always achievable to simplify that. Now what if they give you integral of sine raised to the power of 5x to begin with? Or what if they ask you to integrate sine raised to the power of 6x dx? Or what if they ask you to integrate sine raised to the power of 7x dx? Or what if they ask you to integrate sine raised to the power of 8x dx, and so on and so forth. So to handle all of these things, we got a particular formula which would come in handy to solve questions of this nature. So let me write down formula down. If you were to be asked to integrate sine raised to the power of nx dx, then the formula is negative cos x times sine raised to the power of n negative 1 x divided by n positive n negative 1 over n integral of sine raised to the power of n negative 2 x times dx. Now I can clearly show you the output for this particular. In other words, by applying this formula we can get each of these cases. In other words, no matter what the value of n is, whether it's 5 or 6 or 7 or 8, we can obtain it. Now let me take the simplest one. For n is equal to 2, we are expected to integrate sine squared x dx. Now let me show you this. Now if I were to integrate this, this is going to be 1 over 2, I can take it out. So if I were to take 1 over 2 out, this is going to be dx, integral of dx, negative integral of cos 2x dx, right? So this is going to be 1 over 2 times. If I were to integrate dx, it's going to give me x. If I were to integrate cos 2x, this is going to give me sine 2x. The coefficient of x is 2, so I divide it. Now if I were to distribute 1 over 2, this would give me x over 2 negative sine 2x over 4 positive arbitrary constancy. Okay, now just by applying the formula we will actually get the same quantity. Let me show that to you here. Now this is equal to, n is equal to 2, so it's going to be negative cos x times sine raised to the power of 2 negative 1 times x divided by 2 positive 2 negative 1 over 2 integral sine raised to the power of 2 negative 2 times x times dx. So this is equal to negative cos x. Now sine raised to the power of 2 negative 1, that's going to be sine x divided by 2 followed by a positive sign. 2 negative 1 will give me 1 over 2 integral sine raised to the power of 2 negative 2, that's going to be 0, so that's going to be 1, right? Sine anything to the power of 0 apart from the quantity being, in other words, a raised to the power of 0 will give me 1 for all values except for a being equal to 0, so this will not work out. So in this case a is strictly not equal to 0, right? So having mentioned that, however, there are special cases which I don't want to go. Just for the sake of simplicity, I want to confine myself to quantities which provide me or which produces the value 1. So in this case it's going to be 1, so that would mean I would get a dx here. Now if I were to integrate this, this is going to be negative cos x sin x divided by 2, and the integral of dx would give me x divided by 2. Now there is a formula which we can use. What is that formula? I'm going to multiply this by 2, so it's going to be 2 times cos x sin x, and I'm going to divide by the same quantity, so that would mean I would get a 4 here followed by x over 2. Now I can rewrite this as negative 2 times sin x cos x divided by 4 positive x over 2. Now what is this? Now this is our famous sin 2x formula. So sin 2x is nothing but 2 times sin x cos x. So if I were to use that, this is going to be sin 2x, right, with a negative sign, divided by 4 positive x over 2. So if I were to rewrite it with x over 2 as a beginning quantity, as a starting quantity, I would get x over 2 negative sin 2x over 4 positive arbitrary constant c. So I will draw the red line and I will show you what I have got when I just directly made the substitution. You see that? However, I can understand this requires some steps to achieve the final result, but this is because of the fact that n is 2, right? Now imagine if n is equal to 6 or n is equal to 8 or n is equal to 10 or n is equal to 12. This will come in very much handy. This method will come in very much handy. Now we can take greater values of n and we can apply the formula and see how good the formula is. Students, we will prove this reduction formula. So foremost, what I would like to do is I would like to take, let I suffix n be equal to integral sine raised to the power of n x dx. I will rewrite this as sine raised to the power of n negative 1 x times sine x dx. Then I will make the substitution for u to be as sine raised to the power of n minus 1 x, and my dv to be as sine x dx. Now if I were to integrate this, dv would give me v is equal to negative cos x. If I were to differentiate this, this is going to give me n negative 1 times sine raised to the power of n negative 2 x. Differentiation of sine x would give me cos x. Now using the formula uv negative integral v du, this would give me, of course on the left hand side you got in. My u is sine raised to the power of n minus 1 x times my v is cos x with the negative sign, negative integral v is negative cos x, that's going to be positive here. So I can place that cos x, of course I got a du here, so it's going to be n minus 1 times cos x times sine raised to the power of n minus 2 times x times cos x times dx. So this is what we have got. Now I can multiply these two together. So this is equal to negative sine raised to the power of n minus 1 x times cos x. N minus 1 can be taken out. Now cos x is cos squared x. So this is going to be sine raised to the power of n minus 2 x times cos squared x times dx. So I can rewrite this as cos x with a negative sign times sine raised to the power of n minus 1 times x, positive n minus 1 times sine raised to the power of n minus 2 times x. Cos x, in fact cos squared x can be rewritten as 1 negative sine squared x times dx. So this is equal to negative cos x times sine raised to the power of n minus 1 times x, positive n minus 1. Now I'm going to split this, I'm going to distribute this. So it's going to be integral sine raised to the power of n minus 2x times dx negative integral sine raised to the power of n minus 2x times sine squared x times dx. So this is equal to, I got I suffix n on the left hand side, so this is equal to negative cos x sine raised to the power of n minus 1 times x, and this is going to be positive n minus 1 times integral sine raised to the power of n minus 2x dx, and this is going to be negative of n minus 1 times integral sine raised to the power of n x dx. Now this is nothing but I, because you can clearly see that I suffix n is equal to integral sine raised to the power of n x dx. So I can rewrite this as negative cos x sine raised to the power of n minus 1 x, positive n minus 1 times integral sine raised to the power of n minus 2 x dx, negative n minus 1 times I suffix n. I got a in here, so I will push this to the left hand side. This would give me in, negative would become positive n minus 1 times I suffix n is equal to negative cos x times sine raised to the power of n minus 1 x, positive n minus 1 times integral sine raised to the power of n minus 2 x dx. This is going to be I suffix n, positive n times I suffix n, negative I suffix n is equal to negative cos x sine raised to the power of n minus 1 x, positive n minus 1 times integral sine raised to the power of n minus 2 times followed by dx. So clearly I suffix n with a negative sign and I suffix n can be cancelled, giving me n times I suffix n is equal to negative cos x times sine raised to the power of n minus 1 x, positive n minus 1 times integral sine raised to the power of n minus 2 x times dx. Now what we can do is we can push the n down. So this is going to be I suffix n is equal to negative cos x sine raised to the power of n minus 1 x divided by n, positive n minus 1 over n integral sine raised to the power of n minus 2 x dx. Now clearly you can see this is exactly what we have started with. You see this formula? This is exactly what we have got. So hence the proof is complete. Students, we will move on to the next question. Now having obtained the reduction formula for sine, we have a similar reduction formula for cos, which has given us integral cos raised to the power of n x dx is equal to sine x times cos raised to the power of n negative 1 times x divided by n, positive n negative 1 over n integral cos raised to the power of n negative 2 x dx. Now I'm going to show you how to get this proof, and that is very interesting too. So let us start off by taking I suffix n is equal to integral cos raised to the power of n x dx. This is rewritten as integral cos raised to the power of n negative 1 x times cos x dx. Now let me take u to be as cos raised to the power of n negative 1 x, and dv is equal to cos x dx. If I were to differentiate this, it would give me n negative 1 times cos x raised to the power of n negative 2. Differentiation of cos x is sin x. I got a negative sign here, and if I were to integrate this, it would give me v is equal to sine x. So applying the formula uv negative integral v du, this is going to be u, my u is cos raised to the power of n negative 1 x times my v is sine x negative integral my v is sine x, my du is, there's a negative sign, so this will be positive, so n negative 1 times cos raised to the power of negative 2 times x times sine x times dx. Okay, so there is going to be a dx here. Okay, now this can be further rewritten as sine x times cos raised to the power of n negative 1 x positive, sine x into sine x can be multiplied, so I get a n negative 1, I can take it out, and I have a cos raised to the power of n negative 2 times x times sine squared x times dx. I can rewrite this as sine x cos raised to the power of n negative 1 x positive n negative 1 times integral cos raised to the power of n negative 2 times x. Sine squared x is written as 1 negative cos squared x times dx. This is equal to sine x times cos raised to the power of n negative 1 x positive. I'm going to split it like this. Integral cos raised to the power of n negative 2x times dx. So let me write that, n negative 2x times dx negative integral cos raised to the power of n negative 2x times cos squared x times dx. So this is equal to sine x times cos raised to the power of n negative 1 x positive n negative 1 times integral cos raised to the power of n negative 2 times in fact it's x times dx, and that has to be followed by n negative 1 times integral cos raised to the power of n negative 2 times cos squared x would give me cos raised to the power of n x times dx. Now I can further rewrite this as sin x times cos raised to the power of n negative 1 x positive n negative 1 times integral cos raised to the power of n negative 2 x dx negative n negative 1. Now this is what we started with, right? Can you make this observation? So this is going to be I suffix n. I already have a I suffix n here, so push this to the left, we get I suffix n positive n negative 1 times I suffix n is equal to the right hand side sin x times cos raised to the power of n negative 1 x positive n negative 1 times integral cos raised to the power of n negative 2 x times dx. This can be rewritten as I suffix n positive n times I suffix n negative I suffix n positive I suffix n negative I suffix n will be cancelled, giving me sin x times cos raised to the power of n negative 1 x positive n negative 1 times integral cos raised to the power of n negative 2 x dx. Now I get n times I suffix n. You push the n down, so this is going to be in is equal to sin x times cos raised to the power of n negative 1 x divided by n positive n negative 1 over n integral cos raised to the power of n negative 2 x dx. Now what is this? This is exactly the formula that we started with. You see the sin x cos raised to the power of n negative 1 x over n, sin x times cos raised to the power of n negative 1 x over n, positive n negative 1 over n times integral cos raised to the power of n negative 2 x dx, n negative 1 over integral cos raised to the power of n negative 2 x dx. So we are proved, and this is a good place for us to draw the red line. So we will move on to the next question. Students, this is a lovely proof, so make sure to practice it. Students, having obtained the reduction formula for sin x, for cos x, it's time for us to obtain the reduction formula for tan. So we have a similar formula for tan. It's nothing but integral tan raised to the power of nx dx is equal to tan raised to the power of n negative 1 x divided by n negative 1 followed by negative. In fact, if you are going to be taking it as in, if this is equal to in, then this is going to be I suffix n negative 2 for n greater than or equal to 2. And in fact, you can rewrite it in this fashion. I suffix n is equal to tan raised to the power of n negative 1 x divided by n negative 1 negative I suffix n negative 2. Now furthermore, you can also rewrite this as I suffix n positive I suffix n negative 2 is equal to tan raised to the power of n negative 1 x divided by n negative 1. So this is a beautiful formula. Of course, the condition for n is stated here clearly. Now we will obtain the proof for this. So let us obtain the proof. I'm going to start off by this sentence. Let us consider I suffix n to be equal to integral tan raised to the power of n x dx. Now I can rewrite this as integral tan raised to the power of n negative 2 x times tan squared x dx. Now we know that secant squared x negative tan squared x is equal to 1. Therefore secant squared x negative 1 is equal to tan squared x. So if I were to use the formula here, this is going to be equal to integral tan raised to the power of n negative 2 x times secant squared x negative 1 times dx. Now I can rewrite this as integral tan raised to the power of n negative 2 x times secant squared x times dx negative integral tan raised to the power of n negative 2 x times dx. On the left I got I suffix n. Now this is nothing but I suffix n negative 2, and I've got here integral tan raised to the power of n negative 2 x times secant squared x dx, and on the left I got in. Now I can push this here. This would give me I suffix n positive I suffix n negative 2 is equal to integral tan raised to the power of n negative 2 x times secant squared x dx. Now what I wish to do, I would like to take let tan x be equal to t. I differentiate this, I get secant squared x dx is equal to dt. This is equal to integral t raised to the power of n negative 2 times dt, because secant squared x dx is equal to dt. So on the left I get I suffix n positive I suffix n negative 2. If I were to integrate this, this would give me I t raised to the power of n negative 2 positive 1 divided by n negative 2 positive 1, which can be rewritten as t raised to the power of n negative 1 divided by n negative 1. Now if I were to resubstitute the value for t, which is tan x, this is going to be tan x raised to the power of n negative 1 divided by n negative 1, which can be further rewritten as tan raised to the power of n negative 1 x divided by n negative 1. What's on the left hand side? I suffix n positive I suffix n negative 2. So this would mean, hence we have proved I suffix n positive I suffix n negative 2 is equal to tan raised to the power of n negative 1 x divided by n negative 1. Right? So if you were to check this with this, this is exactly what we have got. So you can clearly say hence proved. Hence proved. So we'll move on to the next question. Students, we have obtained the reduction formula for sin x, cos x and tan x. Now it's time to obtain the reduction formula for cot x. So this is the reduction formula for cot x. So it is given as I suffix n is equal to negative cot raised to the power of n negative 1 x divided by n negative 1 negative I suffix n negative 2 with n greater than or equal to 2. Now this can be rewritten as I suffix n. If I were to bring this to the left side, that's going to be positive I suffix n negative 2 is equal to negative cot raised to the power of negative 1. So that has to be divided by n minus 1. So this is going nothing but I suffix n positive I suffix n negative 2 is equal to negative cot raised to the power of n negative 1 times x divided by n negative 1. So this is the reduction formula for cot, and we will be proving it. So we will start off with this proof as follows. So let us consider I suffix n to be equal to integral of cot nx times dx. Now we can rewrite this as integral cot raised to the power of n negative 2 x times cot squared x dx. But we know that cosecant squared x negative cot squared x is equal to 1. So cosecant squared x, in fact I need to extract for cot squared x, right? So bring this negative 1 to this side and push the cot squared x to the other side. So you got cosecant squared x negative 1 is equal to cot squared x. If I were to substitute that, I would get cot raised to the power of n negative 2 times x times, this is cot, and I need to substitute this. This is going to be cosecant squared x negative 1 times dx. So on the left side I get I suffix n is equal to, if I were to distribute this, this is going to be integral cot raised to the power of n negative 2 times x times cosecant squared x times dx negative integral cot raised to the power of n negative 2 times x times dx. So this is what we have got. Now if actually we have taken I suffix n to be equal to integral cot raised to the power of n x dx. So this is going to be negative I suffix n negative 2, and this is going to be integral cot raised to the power of n negative 2 times cosecant squared x dx, and on the left I got I suffix n. So I can push this here. This is going to be I suffix n positive I suffix n negative 2 is equal to integral cot raised to the power of n negative 2 x times cosecant squared x dx. Now if I were to substitute, I'm substituting here, let cot x to be equal to some t. If I differentiate this, this is going to be negative cosecant squared x dx is equal to dt. So cosecant squared x dx is equal to negative dt. So upon substitution, this is going to be, in place of cot x, I need to substitute t. So this is going to be t raised to the power of n negative 2, and cosecant squared x dx is negative dt. So it's going to be negative dt being placed here. So if we were to integrate this, this is going to be t raised to the power of n negative 1, because you are adding 1 here, divided by n negative 1. But t is actually cot, so there's going to be negative cot raised to the power of n negative 1 x divided by n negative 1. So on the left hand side I get I suffix n positive I suffix n negative 2. This is what I've got. Now let us compare this with the formula that we are aiming at. So this is the formula we are aiming at, right? So what we have got here, we got I suffix n positive I suffix n negative 2 is equal to negative of cot raised to the power of n negative 1 x divided by n negative 1. So just check this out. So we have got the same thing, I suffix n positive I suffix n negative 2 is equal to negative cot raised to the power of n negative 1 x divided by n negative 1. So this is the right place to draw the red line and then state here as n's proved, right? So that is a beautiful result for cot, and we will move on, students. Having obtained the reduction formula for sin x, cos x, tan x, and for cot x, it's time that we obtain the reduction formula for secant raised to the power of n x dx. Now if we were to take this as I suffix n, and that would give us I suffix n to be equal to tan x times secant raised to the power of n negative 2 times, or I should say x divided by n negative 1 positive n negative 2 over n negative 1 times I suffix n negative 2. So this is the reduction formula for secant x, in other words for integral secant raised to the power of nx. So we will obtain the proof for this. So students, we are going to achieve this proof a little bit differently. So what we will do is, foremost we will just take off, let us consider I suffix n to be equal to integral secant raised to the power of n x dx. Now we will rewrite this as integral secant raised to the power of n negative 2x times secant squared x dx. Now what I wish to do is I would like to take, let u be equal to secant raised to the power of n negative 2x, and then I will take dv to be as secant squared x dx. Now when I differentiate this, I would get n negative 2 times secant raised to the power of n negative 3 x times differential of secant x is secant x tan x. Of course I get a dx there, so if I were to rewrite this, this is going to be n negative 2 times secant, I got a secant x and n minus 3, so they can be clubbed, giving us secant raised to the power of n negative 2 x times tan x times dx. This is my du. Now integrating this would give me integral of dv is v, integral of secant squared x is tan x. So let us substitute these things over here. So this is nothing but uv negative integral v du. This is integration by parts. On the left side I get in. So my u is secant raised to the power of n negative 2x. My v is tan x negative, followed by v is tan x times my du is n negative 2 times secant raised to the power of n negative 2 times x times tan x times dx. So let me rewrite it like this. So this is going to be n negative 2 times integral. I have secant raised to the power of n negative 2 x. Tan x gives me tan squared x dx. So on this side you get secant raised to the power of n negative 2 x times tan x. So this is going to be I suffix n. Now what we can do is we can actually rewrite tan squared x, right? So how are we going to rewrite tan squared x? We can we know this formula, secant squared x negative tan squared x is equal to 1, and from here secant squared x negative 1 is equal to tan squared x. So we can make that substitution there. So substituting, this is going to be secant raised to the power of n negative 2x times tan x negative n negative 2 times integral secant raised to the power of n negative 2x times, I just mentioned to you that tan squared x has to be replaced with secant squared x negative 1 times dx. So distributing this would give me secant raised to the power of n negative 2 x times tan x negative n negative 2. This is going to be integral secant raised to the power of n negative 2x times secant squared x times dx negative integral secant raised to the power of n negative 2x times dx. So this is what we've got. Now n negative 2 and a 2 is there, so that would give us secant raised to the power of n x dx with n negative 2. There is a negative sign here, and if I were to bring this negative sign inside, this is going to be positive n negative 2 times. Now we have taken I suffix n to be as integral secant raised to the power of n x dx. So in this case this is going to be n negative 2 times I suffix n negative 2. Now this is I suffix n, right? So let me write this term also. So secant raised to the power of n negative 2x times tan x, and then you get I suffix n. So if I were to bring this to this side, this is going to be I suffix n positive n negative 2 times I suffix n is equal to secant raised to the power of n negative 2 times, or I should say x times tan x positive n negative 2 times I suffix n negative 2. So if I were to distribute this, this is going to be I suffix n positive n times I suffix n negative 2 times I suffix n is equal to secant raised to the power of n negative 2 x tan x positive n negative 2 times I suffix n negative 2. Now I suffix n and a negative 2 times I suffix n, that would give me a negative I suffix n. So I suffix n negative I suffix n is equal to secant raised to the power n negative 2 x tan x positive n negative 2 times I suffix n negative 2. I suffix n can be taken out, giving me n negative 1 is equal to secant raised to the power of n negative 2 x tan x positive n negative 2 times I suffix n negative 2. Now push this n negative 1 to the right side, that would give me I suffix n is equal to secant raised to the power of n negative 2 x tan x divided by n negative 1 positive n negative 2 over n negative 1 times I suffix n negative 2. So this is exactly what we have, right? And this is a good place for us to draw the red line and write hence proved. So this is a beautiful question, and we will move on to the next question. Students, now having obtained the reduction formula for sin x, cos x, tan x, cot x and secant x, it's time that we obtain the reduction formula for cosecant raised to the power of n x dx. If I were to take this as I suffix n, then we would have I suffix n to be equal to cot x times cosecant raised to the power of n negative 2x divided by n negative 1 with the negative sign, followed by positive of n negative 2 over n negative 1 times I suffix n negative 2. So this is a beautiful reduction formula for cosecant raised to the power of nx dx. Students, I would like to give this as a home assignment for you all to try this and get the proof. So now we will move on to the next beautiful question. The question is, if I suffix n is equal to integral cot raised to the power of nx dx and I suffix 0 positive I suffix 1 positive 2 times of I suffix 2 positive I suffix 3 positive etc. up unto I suffix 8 followed by I suffix 9 positive I suffix 10 is equal to a times of u positive u squared over 2 positive etc. up unto positive c, then we are asked to get the value of a. Now where our u is given to be as cot x and c is the arbitrary constant. So this is a beautiful question. Now the most important thing is we have a relationship connecting I and cot, right? So that relationship is, we know that I suffix n positive I suffix n negative 2 is equal to negative of cot raised to the power of n negative 1 x divided by n negative 1, right? This relationship can be rewritten as negative of cot x raised to the power of n negative 1 divided by n negative 1, right? But we are given that u is equal to cot x, so I can rewrite this as negative u raised to the power of n negative 1 divided by n negative 1, and of course on the left hand side I got I suffix n positive I suffix n negative 2. So this is what we are going to use. Now we have got, this is given, I0 positive I1 positive 2 times I2 and so on. Now let me write that down. So given I0 positive I1 positive 2 times of I2. So the meaning is I2 occurs twice. So let me write that I2 positive I2 positive I3 occurs twice, I3 positive I4 positive I4 positive I5 positive I5 positive I6 positive I6 positive I7 positive I7 positive I8 positive I8 positive I9 positive I10 is equal to, of course I am not considering the right hand side, it's understood, the right hand side is featured there. So let me simplify this, is equal to the right hand side, it's given. So let me just place it in the actually, since the space is too limited, I just want to just place RHS there. Now what I want to do is I want to club these terms. So that clubbing is done as follows. So what I would do is I would take I0 with I2. I0 is added with I2, that's fine. Then I will add I1 with I3. In other words, probably this would be a better way. I1 with I3. Okay. And now I've got I2. I would add this I2 with I4. So I2 positive I4. Now I got a I3. I will add this I3 with I5. So I3 plus I5. So that's fine. Now I got a I4 with I6. So I will add I4 with I6. That's fine. Now I got a I5. I will add I5 with I7. So this goes with this. So I5 with I7. Right. Now I got a I6. I will add it with I8. I6 and I8. And then so I4 with I6, that's fine, and I5 and I7, and I6 with I8. Okay, so this is done, this is done. I got a I7, so we need to have two I7s, right? So I will just place to one I7. So two I7s are there. So now I8 is over here. So one I7 is there. So I will just add this I7 with I9. Right. So that's going to be plus I7 with I9. That's fine. And I get a I8 and a I10. So I will add I8 with I10. So that's fair enough. And this is equal to the right hand side. Now we will have to evaluate this. So how are we going to evaluate this? We are going to use this expansion, or I would say this expression, this equation which we have got. So let me name it as 2. Now if I were to substitute I0, right, in fact to get I0 I need to substitute n is equal to 2. So that would give me the first term. So now the thing is that I need to move on to the next page so that you can better understand what we are doing. So let's do that. So I'm going to take n is equal to 2. Now if n is equal to 2, this would give me I2 positive, n is equal to 2, that's going to be I0. This is equal to, I need to substitute n is equal to 2, so it's going to be negative u raised to the power of 2 negative 1 divided by 2 negative 1, which is equal to negative u raised to the power of 1 divided by 1, which is nothing but negative u. So that's fine. I've got I0 positive I2. So next is I1 positive I3. So when would that be possible? To get I1, I would have to take n is equal to 3. So this is n is equal to 2. This is n is equal to 3. If I were to take n is equal to 3, this is going to be negative u 3 negative 1. Right. So that's going to be u squared divided by 3 negative 1 is equal to 2, which is equal to negative u squared over 2. Next, n is equal to 4. N is equal to 4 would give me I4 negative 2 would give me I2, and this is 4. So this is I2 and I4, and n is equal to 4 is going to be negative u raised to the power of 3. 3 negative 1 is going to be 2. So this is negative u cubed over 2. So this is what I've got. Next, n is equal to 5. If I were to take n is equal to 5, I would get I3 positive I5 and negative of u4 divided by 5. 5 negative 1 is 4, so this is negative u raised to the power of 4 divided by 4. So next n is equal to 6. 6 would give me 4 here, and I6, so n is equal to 6 would give me 5 and 5, so negative u raised to the power of 5 divided by 5. Now n is equal to 7, let me use the space here, and that would give me I5 positive I7 is equal to negative u6 divided by 6. N is equal to 8. N is equal to 8 would give me I6 positive I8 is equal to negative u7 divided by 7, and n is equal to 9 would give me 7 positive I9, which is equal to 9 means negative u8 divided by 8, right? So next is n is equal to 10. N is equal to 10 would give me I8 positive I10 is equal to n is equal to 10, that's going to be negative u9 divided by 9. So we got a value for this, 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 for this. So let's substitute that. So if I were to take this as 3, right? So taking this as 3, right, this would give me 3 would now be rewritten as, therefore 3 is rewritten as, substitute these values. So this is going to be negative u squared over 2 negative u cubed over 2, right? N is equal to 3, 3 minus 2, n is equal to 4. This would be 3 here, okay? Just a small correction, this is going to be 3. Okay, so u cubed over 3 and followed by negative u4 over 4, negative u5 over 5, negative u6 over 6, negative u7 over 7, negative u8 over 8, negative u9 over 9, right? So if I were to take the negative sign out, I'm going to take the negative sign out, this would give me u positive u squared over 2 positive u cubed over 3 positive u4 over 4 positive u5 over 5 positive u6 over 6 positive u7 over 7 positive u8 over 8 positive u9 over 9. So this is what I have got. So taking negative 1, now if we were to equate this with the right hand side, so this is equal to, so let me write that down, equating with the right hand side. So what is on the right hand side? The right hand side is actually a times of u positive u squared over 2 positive u cubed over 3 plus etc u raised to the power of 9 over 9. This is the right hand side. So clearly equating this quantity with the right hand side would give us a is equal to negative 1. So that is the solution for this particular question. Thank you students. I hope you enjoyed this particular lecture, and we will meet you all in the next lecture. Have a nice day.